our three-charge system has some energy. Obviously, excuse me, if these charges weren't somehow held down to their points, these two charges would tend to fly away from each other and toward this one. What would happen if we release this system? Well, the energy gives us an idea. What is the energy of the system? We're going to say that the energy of this system is the energy required to assemble the system. And we're going to think of assembling the system as follows. Start out with a blank or an empty space and plop down charge Q1 here. Space is empty, there are no other charges around. We'll plop down the charge Q2 into empty space with no other charges around. If there are no other charges around, it doesn't take any work to get Q2 to where it is. But now when we bring Q1 in from a great distance, or essentially from infinity, we have to do work against the electric field of Q2, against the repulsion of Q2. So we're going to have to definitely do positive work to get Q1 into the system. You recall that a little while ago we actually, I think, determined, well, no, it wasn't, I don't think it was at this point, but we determined the potential required to bring a charge into a point A in the vicinity of a 5 microcoulomb charge. We're going to do something very similar here. Okay? In any case, after we've brought charge Q1 into the vicinity of Q2, we have to bring the charge Q3 into the vicinity of both Q1 and Q2. Since both of these charges are here now, this charge is going to be attracted to both of them as we bring it in from infinity, which means that we're actually doing negative work on this charge to bring it in. That is, these two charges are doing work on this charge. The work that we do is opposite to the work that's done on the charge, and as a result, negative work or positive work is done on the charge. We have to do negative work, and there will be a negative voltage associated with this. So we'll sort that out just using the potential function. So imagine assembling the system in 3 stages. In the first stage, here's our system. It consists of the charge Q2 sitting at a point that we're going to call the origin, and the total energy of the system is 0 because it took no work to get Q2 to where it is. In the second stage of assembly, well, the second stage corresponds to bringing in the charge Q1 to the point, we'll call the point A. It has the same coordinates that we've seen, but we're just going to give it a name, A. And remember that this point is square root of 0.65 meters from charge Q2. And I notice that my square root sign got a little carried away here, so let's fix that. The square root sign was over the meters, and it should not have been. Okay, so charge Q1 comes into this proximity with charge Q2. How much energy does it take? Well, the potential, the electrostatic potential at point A due to the charge Q2 is just KQ2 over R12 over this distance. If we calculate this potential at A due to charge Q2, we get 75,000 volts. We get that very simply. We just plug in the value of Q2 and we plug in the 0.65 meters. This will be our result. The potential energy, therefore, and we're going to call this the potential energy of the system consisting of charges 2 and 1. The potential energy that we have from these two charges is going to be, well, let's see, how can we reason this out? 75,000 volts means 75,000 joules per coulomb. That's the energy required to get charge to point A, if charge Q2 is already there, of course. How much charge do we bring into point A? Well, we brought in the 7 microcoulomb charge Q1. So if we multiply our 75,000 joules per coulomb by the 7 microcoulombs to get 0.53 joules, what have we done? We've multiplied charge Q1 by the potential at A. Since charge Q1 is brought to the point A, and since the potential at A is the work per unit charge required to get to point A, this makes perfect sense. This is how we calculate the potential energy of a charge Q1 at a point A where the potential is 75,000 volts. Okay, now this potential energy, again, is the work required to bring Q1 to the point A. Just as in a gravitational field, if we have to do a certain amount of work to raise an object to a point, we did that work, and that work is now the potential energy of the object. Symbolically, the potential energy, PeQ1, is Q1 times V1, that should be VA, pretty bad looking A, but we'll take what we can get. Okay, Q1 times VA is just Q1 times, well, what's VA? It's KQ2 over R12. Just the calculation we did over here. So when we multiply Q1 by KQ2 over R12, we get KQ1Q2 over R12. In general, when we calculate the potential due to two charges, the potential energy of a two-charge system, that potential energy will just be K times first charge times the second charge divided by their separation. In the next stage of assembling the system, we bring the charge Q3 into a distance of about 0.9 meters from Q1 and about 1.03 meters from Q2. These distances we calculate using the Pythagorean theorem with the coordinates of the 3 points, and that should be very straightforward at this point. Now the idea is going to be that the potential at point B is just the sum of the potentials. That is, Q3 requires a certain amount of work, and in this case has a certain amount of work done on it to come into the vicinity of Q1, and a certain amount to come into the vicinity of Q2. And we just calculate those two potentials, the two corresponding potentials, as if, well, we calculate the potential with charge Q2 as if charge Q1 wasn't there. Then we calculate the potential of charge in relation to charge Q1 as if Q2 wasn't there. And those quantities will be KQ2 over R23 and KQ1 over R13. When we plug the numbers in, we're going to get 44,000 volts and 50,000 volts, or 94,000 volts. So that the potential energy, PE23, potential energy of charge Q2 in relation to charge Q3 in relation to charge Q2, and PE13, the potential energy of Q3 in relation to Q1, is just going to be the negative 12 microcoulomb of the charge Q3 times the total potential, which is the 94 kilovolts, and we end up with a charge of, or a potential of negative 1.1 joules. As a result, the total potential energy of the system will be the sum of the three potential energies of the three pairs of charges. Potential energy between charges 2 and 1, between charges 2 and 3, and between charges 3 and 1. And that potential energy is the 0.53 joules minus the 1.1 joules, or negative 0.57 joules. Now this negative work means that negative work, we have to do negative work in order to get this thing in here. This means positive work is being done on the charge by the field, which means that if we did this right, we could get 0.57 joules of energy out of the system during assembly. Okay, this charge is being pulled in here. If we could harness it to some kind of a generator, we could get this much energy out of the assembly of the system. And if we want to disassemble the system, remove these three charges back to an infinite distance, we have to do 0.57 joules of work in order to disassemble it. It won't fly apart by itself. We won't get energy out of it. We'll have to do work in order to disassemble it. If the total energy of the system was positive, then we would have to do work to assemble it. And if we allowed it to disassemble, or if we disassembled it, we could harness it up and get the opposite amount of work.